In this video, we are going to see an example of how insertion works in a B tree. So here I've taken a simple example, which is we have a 2-3 tree. A 2-3 tree can have maximum 2 items per node. So in this case, like all of these nodes have at most 2 items. Also, it can have maximum 3 non-null children per node, which is, you can see like this has 3 children right now. So what happens when we insert one? So the way we insert elements in a BST is basically we do the same thing which we did in BST. We try to find the element which is 1 is less than 5. So we are going to go towards the left. Now we have reached the leaf and we always add element to the leaf. That's how it's going to work. So we add one more node here, which is we have this node, but we add one more key to this node, which is 1. Next, now this node, which is like once we have added this 1 to this node, the first property gets violated, which is the number of items per node should be less than 3, but now it has 3 children. So we are going to split this node. So how this works is you move the central element to the parent node, which is in this case 1 and 4 will be standalone new nodes, and 3, which is the central element, goes and to the parent node, which is in this case, now the parent node will have 3 values, which is 3, 5, and 7. 6 will still point to between 5 and 7, and 7 will now start pointing to its previous element. So otherwise everything remains the same. We are going to see an example here. So how the split works is you move the 3 to the top, and then the 3 is moved right here. Now the issue is like when we try to move 3, this particular node defies both the properties, which is you can have maximum 3 non-null children, but now we have 4. Also, you have maximum 2 items per node, but now we have, instead of 2, like 3. So we fix that again similarly, which is we move the central element to the top. So it will look something like this. It will split the node into 2, which is 5 and 7. And now 7 will have no left children. It will have one left child because 6 is on the between 5 and 7. So it will look something like this. And 3 will have 2 childs, which is 1 and 4. So this is how it's going to look like after the final insertion. You can see that it still satisfies the BST property, which is everything on the left is less, everything on the right is greater. Also, you can also identify that the height is still perfectly balanced, which is we didn't need any rotations, but still it kind of worked, which is it just increased the height by 1 because we now have some split operations. So whenever we try to insert a new key into this B tree, it only increases the height by 1, and but it's still, the tree is still pretty balanced. So now we are going to discuss what are B plus trees. So I want to also distinguish between what are B plus trees and what are B trees. So they are kind of similar, but they are extended versions of B trees. And this B plus tree is the most frequently used tree out of all this B tree family, because it has a very specific use case, which is it is used in databases and file systems, and it's very fast. Also, when you design a memory, like these B trees are used. We are going to see an example very soon. But what is the core distinction between a B tree and a B plus tree is that in a B tree, you see that like whenever we had some nodes that were exploding, which were like these leaves were turning into, they were overfilled, we were splitting the nodes, and the splitted node went up. In a B tree, the leaves contain all the keys, which is like all these keys which are on, which have been moved up, a copy of them is kept in the leaves. So the leaves contain all data, even like duplicates of that data, and there's some value to it. We are going to discuss when we discuss our example. But basically, like when you see, like even in the previous example, we saw that uh, like in this case, 134 was getting filled, uh, and 5 6, like whenever we try to insert 5 6, although there was a split that happened, 5 is still there in the leaf node. So you keep a copy in the leaf node. So the leaf node have all the data. So basically, the top level nodes, which are all the internal nodes, are just used as indices for movement or search, like to move left or right. But if you want to traverse all the data in the tree, you can still move that through the last particular level, which is just traversing the leaves. And the second change between a B tree and a B plus tree is that the last level, which is all the leaves, are connected through a single or doubly linked list. Some books refer to doubly linked list, some to single linked list, but they are connected. And this is very beneficial when we are like traversing a particular tree, which is in this case, let's say if we wanted to print all our data, we don't need to, like let's say if you were to do an in order traversal, we don't need to go left and right. We can just print it using the head of this particular linked list. So again, just to sum up, B trees store all the data that is stored in the leaves. Plus, uh, B plus trees are basically B trees that store extra data in the leaves, and the leaves have pointers to the leaves forming a linked list for faster traversal. So this is another example of a B plus tree that's given to you. So you can see here, I don't know if you can see here or not, but you can see this 168. You're keeping a copy of that right here as well. You are keeping a copy of this in the nodes below as well. While in a B tree, like this is a B plus tree, in a B tree you wouldn't see copies. You'll just see one particular uh, like of all the non-internal internal nodes, like you will see that we do not have the copies of those non-internal nodes in the leaves. That's the gist of it. So let's see a quick example of how the B plus trees insertion works. So there are two different like conventions. Some books follow that, and like I'm going to follow some other type of convention. It might be available in some other books, but I just wanted to warn you that, like, let's say if you have this B tree, B plus tree, this has n equal to 5 and l equal to 5. So usually when we talk about B plus trees, L could be in like 10,000s or millions, which means the leaves have all the data and they have like millions of keys in per node. So here, now since n equal to 4, it can have at most 4 children and 3 keys in a non-leaf node. And for L equal to 5, it can have at most 5 keys in a leaf node. So let's try to insert the value here called 40. So we are basically inserting a value 40. So the insertion works exactly the same, which is you compare 40 with the root node. Now since 40 is on the right of 30, so we are going to go here. 40 is between 35 and 65, 60. So we are going to go to this node. And now we are going to add that right here. Now you can see that this node has, like we have inserted 40 as into the leaf, but now this node defies the first property, which is uh, the second property, which is it can have at most 5 keys. Now it has 6. So we are going to perform again the split operation, and we move the central element to the top, but we also keep a copy of the central element in the node that we have splitted, which is in this case, we have now these two nodes. But you can see that we have a copy of this 55, like although we move 55 to the top, you keep a copy of that in the splitted node. You can move either of the central elements, like this is a case of odd, so you can move either 50 or 55. I'm moving the rightmost one, which is the center to right. So just stick to one convention if you see these questions in exam. So you move 55 up. So this is just applicable for the leaf node because we want to keep a copy of the leaf nodes on the top. Next, we see that this particular node now defies property 1, which is it can have at most 3 keys in a non-leaf node. So this is a non-leaf node, and now it has 4 keys. So we are going to again perform a split operation, but this time we do not want to copy the central element, because that central element, which is like in this case the central element is 60, because I'm following the right convention in case of odd nodes. So I'm going to move 60 up, but we do not need to keep a copy of 60 here. That's the gist of it. Like some books might be keeping a copy here as well, but it's not required, because we know that the 60 is going to be somewhere in the leaf, and we just want to maintain a track of that value is there in the leaf or not. So in this case, we splitted the nodes. It is now exactly working for any of the internal nodes. It's working exactly the same as B trees, but for external nodes, which is leaf nodes, we have this additional copy step that you need to make sure. So here, now once we did that, we now move to the root node, and we see there's a violation here, because it has, like, the internal nodes can't be greater than 3. Now it has 3 nodes. So we are again going to perform a split. 30 will move up. So it will look something like this: 30. And then you have 10 and 20. And then 60 on the right. That points to these values. So in the next video, we are going to see a few examples of what sort of questions that you can be asked. And we'll also discuss a common use case of where these trees are used.